Yeah, I know. It's one of the
You got me all tied up. I can't even move, you know?
It's one of the biggest student things today.
Don't get me started. I'll just start cussing and the camera's rolling. So the good news is your exams are coming back today, if you stick around for them. The way this goes, don't get sticker shock. If your rate is low, that's why we do retest. You got plenty of time to do it. You can come in and retest at office hours whenever you're ready. If not, right at the end of the semester, before we do final exams, I'm going to take a lecture day and not lecture and allow you to come in and retest. So you've got that option as well. All right? Yeah.
Are you going to curve a little bit, or?
I shouldn't need to with the retests. You guys come in and you retest, you should be just fine. And I don't want to curve because, you know, if you miss problems, I want you to make right on it by coming in and proving that you can do the problem right.
So you say we could retake anytime we want during the semester?
Yeah, whenever you're ready, whenever you feel like you've, figured out what mistakes you made and you're ready to come in and do it again, let me know.
Can we, what's your are you giving us a test today? Or test today?
I'm going to give you the test back today. I don't want anybody retesting today. I need a little bit of time to put together the new exams. When I retest you, the problems are going to be a little bit more difficult than the original ones. Not a whole lot more difficult, but they're going to be more difficult.
They're going to be the same format?
So essentially, you'll be quizzed on the same subject matter, but the difficulty level of the questions is going to be a little different. They'll be a little harder on the retest. Okay. Yeah.
And
let's say we do a little bit worse on the second test, will you take the highest test or just the new?
If you do a little bit worse on the second test, you have to be an English major. That's how it works. I'm just kidding. You shouldn't do worse on the second test. You should only do better. That's how this works, right?
so what if?
What if?
Yeah, what if?
How do you feel about teaching English?
Do you take the highest grade? Or?
Yeah, I'll take the highest grade. Essentially, the problems that you did well on, you're not going to retest on. And the scores that you got on those problems, you keep. The problems you did poorly on, you get to retest. And so if you do better, then we boost your score based on that. All right? I don't want you retesting on the problems that you've already taken.
Okay.
Yeah.
So each retest is tailored to a specific person, or is it just
Yeah, let's say that you got the calculation of the hydrogen orbitals wrong, right? And you missed 20 points on that problem. You're going to come in and you're going to retest on whatever question I replaced that one with.
Okay.
Yeah? Okay, so I don't know how many of you guys missed lecture on Tuesday, but we went over a fairly thorough overview of thermodynamics. And I didn't get it on video. And so right now, before I start, we're just going to be expanding on thermodynamics. But before we start doing that, I just want to review what we discussed last time. So Tuesday, we started with the first law of thermodynamics. First law is conservation of energy. A mathematical statement of the conservation of energy. If you have a universe that's composed of a system and everything else, the surroundings, the energy content of the universe is constant. So you can say it's So delta U, change in the energy of the universe, is equal to delta U of the system plus delta U of the surroundings. For conservation of energy, that means the sum of those two is 0. Therefore, in any kind of a process, a chemical process where energy is exchanged, we have the delta U of the system is equal to negative delta U of the surroundings. Right? It's conservation of energy. Energy can't be created or destroyed. The energy content of the universe is constant, blah, blah, blah. That's first law. Okay? And then we went in and we talked about energy storage. And this is where we're going to kind of focus today's conversation. We're going to do a few delta H calculations, but we're going to talk about the kinds of energy or the ways that energy are stored in the different systems that we do calculations on. I listed several in the last lecture. I just want to focus on the ones that are most relevant to today's discussion. One thing that you should always look at when you look at molecules, a question that you should always be asking yourselves, are what are the kinetic and potential energies of the electrons in the orbitals that they're allowed to be in? We looked at atomic orbitals. There's atomic orbitals or orbitals when you only got one atom. When you have multiple atoms, you've got molecular orbitals, and these orbitals extend over the entire molecule. Either way, when you're looking at electron orbitals, you need to be concerned with the kinetic and potential energies of the electrons. In general, if you have tighter binding and you have negative charge, the electrons moving closer to the positive charge, you've got lowered electric potential energies. And so when energy is released in reactions, oftentimes it's because these electric potential energies decrease. But you also have kinetic energies. Weird thing about orbitals is that when they get smaller, the kinetic energy of the electron increases. And when they get larger, the kinetic energy of the electron decreases. And so you can, it's a weird thing because the smaller the orbital is, usually the lower the electric potential, but the higher the kinetic energy. Anyway, point one, we look at kinetic and potential energy of the electrons in the orbitals. All right? That's a big one. One of the other kinds of energy storage that we ought to look at is potential energy of atoms or molecules approaching each other in space. We're going to look at a problem that relates to these kinds of energies, but an example of this kind of potential energy, and the one that I gave you in class on Tuesday, was water dipoles. When you have water molecules that are stacked up on top of each other, the positive side of one pointing towards the negative side of the other, you've got a lowered electric potential because of the proximities that those two molecules have with respect to one another. When the positive side of one dipole and the negative side of the other dipole approach, they go to lowered electric potential energies. And so the take-home message for this is that when you have condensed phases, condensed phases mean solid and liquid. You've got interactions of charge distributions in such a way that when the molecules approach, they can lower their potential energies. We're going to go into more of this next week, but non-polar interactions, these van der Waals interactions that hold the long hydrocarbon molecules together, these are examples of these kinds of potential energies. And also the dipole interactions in water that cause water molecules to be attracted, those are examples of these kinds of energies. Anytime you've got solid phases and liquid phases, you have large attractive forces between the molecules that are close together. these kinds of forces aren't so important when you're in the gas phase. It's another kind of energy that we need to think of when we're looking at molecular systems. And that is the kinetic energy of atomic and molecular motion. So molecules and groups of molecules, collective groups of molecules, can vibrate. So a single molecule or even a group of molecules can vibrate together and they store kinetic energy in the form of their vibrations. They can translate. So instead of a vibration about a bond, you might have a heated gas phase molecule developing a bunch of translational kinetic energy through motion. And single molecules, not in the condensed phase, but in the gas phase, can rotate. So molecules store kinetic energy in these ways, in all of these ways, and or not kinetic energy, but kinetic and potential. And when those energies change, there's necessarily energy exchanges during any kind of a process where the energy changes. So these are the ways that these guys store energy. And the next question that we asked was, why do we care? Who cares about energy? Well, there's a very important reason that we need to care about energy, and it's the second law of thermodynamics. And basically, the second law of thermodynamics says that the disorder of the universe increases. Tends to increase. And so, based on that second law, we went through and we tried to do a calculation for the total change in the disorder of the universe. We said a couple of things. We made a mathematical definition that was a little bit heady, and it said that the change in the entropy of a system, delta S, is going to be equal to Q over T. So a system or a surroundings, any body. And what that equation said was that this Q represented energy transfer. When a system or a surroundings or whatever it is takes on energy, it gains disorder because that energy allows it to excite states and essentially what entropy means is that you have a lot of different ways to arrange yourself and be at the same energy content. And when you gain energy, you gain ways to spread that energy out amongst all the molecules that are in the system. And so a positive Q taking on energy is going to create more disorder in the system. The T in the denominator there basically just meant that a given heat transfer or energy transfer would create less disorder for a system that was already at high temperature and more disorder for a system that was at low temperature. Low temperature systems are already very highly ordered. Any incremental increase in energy for a low temperature system is going to result in a large increase in the disorder in that system. This is all heavy. We're not going to ask any questions about entropy on exams. But what comes next is very important. Not the derivation, but the take-home message. So we went through and we said, to analyze whether or not a process is going to happen, we got to figure out whether or not the disorder of the universe is going to increase. And so we wrote an expression for delta S of the universe. It's going to be equal to delta S of the system plus delta S of the surroundings. Now for the system, we're just going to assume that we can go in and we can analyze that piece of matter and figure out how much disorder there is in it. And experimentally, that's actually possible. And mathematically, it's possible. So let's just assume that we can analyze our system and we can know how its entropy changes from one state to another. What's more difficult is to understand how the entropy of the surroundings changes. And so we wrote this expression out in a second way. We said this is equal to delta S of the system plus Q of the surroundings over T, the disorder of the surroundings, or the entropy of the surroundings. But we made an argument that this Q of the surroundings is related to things happening in the system. If the system absorbs energy during a process, then energy has been lost by the surroundings and given to the system. If the system releases energy, then energy has been lost by the system and gained by the surroundings. And so on some level, we can tell something about entropy in the surroundings by watching energy flow from the system. Okay? So from there we said we need some kind of a mechanism to determine what the energy exchange was with the system. And we'd be tempted to use delta U of the system, which is equal to U of the system final minus U of the system initial. And therefore, if we could see how the internal energy of the system changed, a positive increase in internal energy would correspond to an increase in energy of the system. A negative delta S for the system would correspond to a release of energy of the system. But there was a problem with that. You can't just look at the total internal energy from the system in the beginning and the end and figure out how much energy has been removed from or put into the surroundings, because systems, any system of matter, when it goes through a change, tends to expand or contract. And when it does that, there's an exchange of energy based on work. So if a system expands, it spends energy pushing against its environment. If a system contracts, it gains energy as its environment pushes against it. And so this internal energy function wasn't the best mechanism for figuring out how much heat entered or left the surroundings. So we put together this new function. We said H is equal to U plus PV. And delta H then was going to be equal to delta U plus P delta V for a constant pressure process. And this function that we put together, it's called the enthalpy, and it corrects the energy exchange in the system to account for energy spent or gained by expansion or contraction. I know this is all very heady, but all you have to remember is this part. Your delta H function here, once it's all been accounted for, tells you how much heat enters or leaves the surroundings. If you know what the delta H of the system is, delta H of the system will tell you whether or not the surroundings gained disorder or by gaining energy, or lost disorder by losing energy. And so back here in our equation, we can replace this Q of the surroundings with negative delta H of the system. And we get this expression. We're going to say that we want it to be greater than or equal to 0 for a spontaneous process, because the disorder of the universe has to be growing. We'll take that whole expression and multiply it by negative t. That changes the sign on that inequality, and the expression becomes delta H of the system minus T delta S of the system. And this is the famous Gibbs free energy system, or Gibbs free energy expression, delta G. Delta G is what all of chemists use to predict spontaneity for processes. They take a look at the magnitude and the sign of delta G. If delta G is less than 0, then you've got a spontaneous process. This indicates that the disorder of the universe is increasing. If delta G is greater than 0, this is a non-spontaneous process, and it occurs there. It means that the entropy of the universe is increasing or decreasing. the end of the day, it's all really just about energy transfer, right? It's about energy transfer and the effects of that energy transfer on the surroundings, spontaneous reactions. All right, so now for practice.
So,
Yeah,
I don't think you explain what's U, what's H, and what's G. Did you?
huh?
Did you explain what's H and U? And
Okay,
G in the
so U is the internal energy. It's the energy of the system or the surroundings. In this case, we're talking about the internal energy of the system. So internal energy is stored in the form of kinetic energy, potential energy, et cetera, in those different forms. If we want to look at and see how energy has moved from the system and the surroundings, you might be tempted to look at delta U. If you look at of the system, if you look at delta U of the system, you can see how much energy the system has in the initial state and how much it has in the final state. The problem with that is that not all of the energy associated with delta U ends up being or affecting the surroundings. There's PV work that gets done, and so energy gets spent in expansion or contraction of the system, and so this delta U does not really represent energy transferred to the surroundings or from the surroundings. If we instead change this expression slightly and make up a new expression that says H, enthalpy, is U plus PV, then when we take delta H, it kind of, this mathematical statement kind of magically accounts for all of the expansion contraction work. And so delta H is a true measure of the heat that enters or leaves the system in a process.
why you put minus before the delta?
That's just because I had a negative delta H over there, and I wanted to get rid of that negative sign. It's just the way that they arranged the thing. They put the expression together. Anyway, take-home message. When you've got heat that is released by the system, that heat, that H, enters the surroundings and it increases the disorder of the surroundings. When energy leaves the system, leaves the surroundings and enters the system, that would correspond to a positive delta H of the system. Then the entropy of the surroundings decreases and the entropy of the system goes up.
You write it down?
All right, so let's go to some problems. So, find the problems that I was going to do here.
Anyone know this?
Couple things. You're going to be doing these calculations on your exam. They're really simple. You're basically going to go look to tables, and tables are going to list these things called delta H naught of formation for a bunch of different species. And the formation enthalpies you can think of as the change in the heat, the change in the delta H when a species is made from its elemental precursors. We adopt a convention we talked about that the formation enthalpies of all atomic species, pure substances, all pure substances are 0. And so we use that as a reference, and you go out and you take different molecules and you form them from their elemental precursors. You monitor the delta H of that reaction, and it gets tabulated as a formation enthalpy for that species. You can use the changes in those formation enthalpies to figure out the change in enthalpy of a reaction. Yeah?
Is that just delta HF or I don't know what
That's
you wrote.
delta H naught of F. Okay. One problem. Let's do this. You go look up in a table formation enthalpies of benzene in the liquid phase, C6H6, we'll call this liquid. You're going to get delta H naught of formation is positive 49, and that's kilojoules per mole. So positive 49 kilojoules per mole. You take C6H6 in the gas phase, look up its formation enthalpy. you're gonna get positive 82.93. Oh, sorry, positive 82.93 kilojoules per mole. We can use those formation enthalpies to figure out what the change in enthalpy is when liquid phase benzene goes to gas phase benzene. You say delta H of the reaction is equal to H of the products minus H of the reactants. Remember, those formation enthalpies need to be multiplied by whatever stoichiometric coefficients are present in the balanced equation. In this case, it can just be 1. For this process, C6H6 liquid goes to C6H6 gas. Delta H of the reaction is equal to H naught of formation of C6H6 gas, which is the product, minus H naught of formation of C6H6 liquid. And so that is 82.93 minus a positive 49. So what is that, like 34? 34 kilojoules per mole. So the positive sign of that delta H indicates that to go from liquid phase benzene to gas phase benzene, you have to absorb some amount of energy. You have to have a positive delta H, and so you have to dump energy into this system. Anybody want to take a guess at why it takes energy to move from the liquid phase of benzene to the gas phase of benzene? We need to pay attention to the potential energies of atoms or molecules approaching each other in space. When you have benzene molecules in the liquid phase, they are at low potential energy because they've come together under the forces of their attractions. And so if you want to take what was in the liquid phase, which is a low potential energy, and move it into the gas phase, which is a high potential energy, you're going to have to separate those molecules against their attractive forces. And so the positive delta H on this reaction is an indication that the system is moving to higher energy, higher electric potential energy. All right? Let's look at another one. You go look up the formation enthalpy of calcium chloride solid, CaCl2. It's going to be negative 795.8 kilojoules per mole. You look up the formation enthalpy of calcium 2+ ion, aqueous. This is a calcium ion that's dissolved in water. You're going to get negative 542.83 kilojoules per mole. You take chloride ion, Cl- in the aqueous phase, and you're going to get negative 167.16 kilojoules per mole. Write the balanced equation. We'll say, we'll call this for the dissolution of calcium chloride. CaCl2 solid goes on to form Ca2+ aqueous plus 2Cl- aqueous. All right? Delta H of this reaction is going to be 2 times the H naught of formation of Cl- plus 1 time the H naught of formation of Ca2+ minus the H naught of formation of the reactants. So minus a negative 795.8. Sorry, I should say minus H naught of formation of CaCl2. Dropping these guys down, you've got 2 times negative 167.16, whatever that is, plus 1 times negative 542. And then